Let's use Faraday's law to build a linear generator. So here we have two rails similar to the rail gun, but now we have a resistor across it and a rail that we will pull. The magnetic flux is into the page, into the minus z direction, and it's constant everywhere. Let's apply Faraday's law and let's integrate counterclockwise around our circuit. So your right thumb points in the z direction, so this will be minus d psi dt in the z direction. So z is pointing out of the page, and so this becomes minus d psi dt out of the page, which is equal to plus d psi dt into the page. The flux into the page will just be B times this area, which is x times L. B and L are constants, so this just becomes BL times dx dt, and dx dt is just the velocity with which we are pulling the bar. So now assume negligible resistance for the rails and bar, so the integral of E dot dl around our circuit will just be I times R. So pulling this bar with a velocity u, you will generate a current flowing through your load resistor R of value BLU over R. So the electrical power delivered to your load resistor is I squared R. So squaring I and multiplying by R, we get B squared L squared U squared over R. Because there's a current flowing in this bar, it's going to experience a force. And the force will be the integral from 0 to L of I dl crossed with the magnetic field. So there will be a force of magnitude I times L times B in the minus x direction. So to move this bar with velocity u, you have to apply a force to overcome this force F sub m. So the force you are applying is I times L times B in the x direction. So when you move the bar a distance dx, you do some work. The force times that distance dx. So the mechanical power you are supplying is dw over dt, so that will be ILB times the velocity with which you're pulling the bar. So for the current, let's substitute in BLU over R. So the mechanical power that we are providing is the same as the electrical power going into our load resistor.